All right, so we'll start. Welcome everybody to the 14th edition of our Meetup, IXIA. First of all, I want to thank PhotoRoom for hosting us tonight in their very brand new offices. You've been here for about a month, so I believe we're one of the first events to be here, so thanks very much. First one? Okay, first one, cool. And I want to congratulate all of you for being here in person tonight, because as you know, there was a bit of a shotgun last week on the tickets. They left in 30 minutes or so. So congrats everyone for being there on time and shotgunning the whole event. I hope you're going to have a lot of fun. For those who don't know me, I'm Sophie Monnier, ex-2009, and I've been the president of IXIA for the last 5 years. First of all, a question that I ask every time. Who comes to IXIA for the very first time tonight? Maybe 20%, 25%, okay. So welcome to everybody that don't know IXIA, and welcome to all of the people that I know already and that follow faithfully the Meetup. For those who don't know us briefly, what's our vision at IXIA? It's actually a double vision. The first vision is to gather the community of École Polytechnique students and alumni that work or are passionate about the field of AI. There are many of us in many companies, and the purpose of this meetup is to gather us to be able to exchange on the state of the art, on the exciting new topics, and have cool conversations at the cocktail. The second vision is a strong no bullshit policy. So all of our board, all of our team does a lot of work to select the themes which are the most exciting for us, and we dedicate a lot of work to find high caliber, good quality speakers, and we spend a lot of time with them to prepare the talks. The speakers can vouch for that, and we hope that you will appreciate the quality of the talks tonight as well. This is our team, so this is not the work of only one person. We have the core team that has been with us for all these years now. And we also have the joy of welcoming a few new joiners since the last edition. So welcome to Stéphane, Nicolas, Jacques, Stanislas, and Sébastien, who are going to help us on this edition, but also the future ones. A few numbers about the group health. So for those of you who might not know, we are present on 4 communication channels. So the AX, this is reserved for students and alumni of École Polytechnique. We are also on Facebook and LinkedIn. So we have had quite a bit of a jump on the AX since the last edition, which is cool. We are nearing 1,000 members. Our last channel is Discord. We don't have so many people on it yet, but I strongly encourage you to join this channel, and I'll just tell you why in a minute. We are the 8th largest AX group today, which is quite cool considering that we are very young. We have existed for only 5 years. But it's also very sad, because you might not know, but there are over 40,000 people on the AX annuaire, and only 2% are part of IXIA. But we think that actually many more than that are going to be interested because they work in AI or we are affected by it. So you can also spread the words about our group. So if you have people from your promotion or colleagues that work in that field, tell them to join the group so that we can find new speakers and new people to attend our events also. So I was saying this is our Discord. Basically, we have a lot of channels where we can communicate. So we have, for example, a job one where all of you can post your different job offerings, or if you're looking for particular kind of jobs, this is a good way to activate the community. And we also have a few more dedicated channels like LLaMA. We've been requested with one on prompt engineering, time series, computer vision, and any other that is actually interested to you. So I would strongly encourage you to join this group and write to us so that we can actually really activate our community. Before I finish, a few quick news that might interest you. First of all, a few podcasts that we have in France that you might want to listen to if you don't. One of them, Data Driven 101, is led by one of our camarades, Marc Sanselme, X2012. Marc is here in the room. Where is he? He's there. He's over there. Hi, Mark. So he basically interviews people in the French ecosystem, either CEOs, CTOs, CSOs, and whatnot. And so far has interviewed companies like L'Oréal, Spotify, Narix, JC Deco, and others. And there's another one, Comptoiria, which is a little bit more high level, but that has featured a few Polytechnique people like Stanislas Polou from Dust or Pablo Ducru from Rave. Pablo is here somewhere in the room tonight at the back. He's over there. So you might be interested to listen to this podcast or even be featured if you're a company and you want to talk about it. Second news, I don't know if you guys know, but I've talked recently to Stéphane Requenat from Jancy. So Jancy is the largest national HPC equipment. It was created in 2007, so they own, among other things, the Janzé supercomputer, but not only that one, others also. What you might not know is that you can have free compute available for you for open research projects. So if you aim to publish or open source your code, this is a cool way to have free compute. Free compute is always nice. The link is here if you want to apply. I believe they have some free link for a given number of CPU and GPU hours. And if you want more, you can apply twice per year for and defend your project. But this is a good way for you to have a compute available if this is an issue for you sometimes. And finally, Ixia is currently shifting gear and becoming an association, actually a proper Loi 1901 association, with myself as president, Frédéric and David as vice presidents, Stéphane and Jacques as secretaries, and Jonas and Sébastien as treasurers. Why are we doing this? Just so you know, basically we want to accelerate Ixia. So far we've done 3 to 4 events per year only. But the field of AI is accelerating. We are all experiencing it this year, and Ixia also needs to accelerate. So we want to do 6 to 8 events per week and also create a few more dedicated streams on Gen AI, on NLP, computer vision, different formats. And so we want to give ourselves the means to present more events to you. So this is ongoing. All right, that's it for me. Tonight we have great speakers. So we will first have, just after me, Mathieu Rouif, the CEO of PhotoRoom, who is hosting us tonight. So he will present to us briefly the company. Then Benjamin Lefaudeux, Guillaume Lample, and a few startups who are going to give us super cool short pitches.
Good evening, everyone. Thanks, Sophie. Thanks for organizing. Thanks for everyone for coming, and thanks Raphael and the PhotoRoom team for putting this amazing space. So yesterday night there were tables all over here to work, and today we work up there. So it's a kind of a big first for us, and we are super happy to host you here. And also, we are happy to host you in English. We have like more than 15 nationalities at PhotoRoom, and that's important for us that we are inclusive and that no one non-speaking French feel excluded for the event tonight. So that's why we're English tonight. So first, I will tell you a bit more about the PhotoRoom story, the inception, as we say. Then do a quick demo, but the most important part is Ben. After me, we'll show a bit more of the secrets of how PhotoRoom works. So PhotoRoom is the #1 AI-driven photo editor in the world. There was a recent benchmark from A16Z, Anderson Horowitz. We are like number 6 in the Gen AI software in traffic, above Midjourney, so first in the photo side. So we're really proud to be here in Paris to develop this new tool that's changing the life of millions of users. And to start, I'll tell you a bit more about the story and how we got started with Elliot. So this is me with a bit more hair, a bit less tired, before kids and before PhotoRoom. And the inception is, well, I was in a GoPro, so GoPro had acquired the startup I was working at, Stupeflix. And on this very nice day, I received an email from Apple. And what they told me is, well, the app I was working on, if I can make... Yeah, the app I was working on, Quick, that's still on the store, was going to be featured by Apple. So big event for app makers. I don't know if there are people in the room who develop apps, but that's kind of big. You get millions of users to your product, so it's quite exciting. So big news, and I look on my side in the GoPro office, newly acquired, to another Mathieu, and I'm going to ask him like, okay, let's do a design as Apple is asking, and let's get featured. Let's get millions of new users. And well, the problem is we had a part-time designer, and actually Mathieu was not here. So that's a problem. I need to do something for tomorrow. And I tell myself, well, when I was at Polytechnique, I learned to use Photoshop. It's been 10 years. I'm good with computers, and let's pull out Photoshop, open Photoshop. But well, what happened is, I mean, millions of buttons. That's the hundreds of buttons, difficult to use. I'm overwhelmed with options. And I ended up spending the afternoon doing something that wasn't very good, and got quite frustrated. And it didn't make sense. Like it should be easy today. It's easy to program apps. It should be easy to do visuals. And that's the founding story of PhotoRoom. And the rest is the rest is history. We got started with Elliot, my co-founder, and we started working on a small app in 2019. And that was that's how we got started at PhotoRoom. And what we did first is we believe a lot in user testing, in talking to users. And so we would go in the street and actually buy McDonald's meals to people in exchange for testing the app. So, and what we realize is, we realize it's not only like a product manager problem to do good visual and fighting with Photoshop. We realize it's everyone's problem. Like people are selling on Le Bon Coin, people are selling on Depop in the UK, Poshmark, eBay. They all need good photos, and actually, it's a problem to create good photos. It's difficult. It's also a problem for chefs who want to spend their time cooking, but they need good photos on Google Maps of their dishes. Jewelry makers, they need good photos too. So it's actually a 500 million people problem that we were starting to solve. And we're just two, so the team grew. There are 500 million people selling online, and that's the beginning of the growth of PhotoRoom. And to add just one thing, a quick number for today. Do you know how many of how much of e-commerce is done on a smartphone today, like the transaction? Maybe someone in the room, not the PhotoRoom people because they all know. Anyone? Yeah. Yeah, that's actually very accurate. It's 72% in worldwide. Was it written? Like I didn't look at the. Oh, okay. Yeah, you jumped it. Okay. 72%. It's more than 80% in China, for instance. And well, what does it look like to do e-commerce on mobile? Yep. It actually looks like this little screen. So it's a big photo, a price, and a buy button. So all that matters now is the photo you get of the product. It's not your template, your layout of your website. It's really like this beautiful photo that inspires trust, and it's very difficult for people to do it well. And that's why we help them. Like people don't have time or the skills to learn it, and PhotoRoom like really helps all the entrepreneurs in the world to do that very well. And that's what we do. Like that's our mission: empower anyone to do Nike level, studio quality level ads and creatives. So and actually that's why we just crossed last week 100 million downloads for PhotoRoom. So I've heard around the room 50 million. That's just under it. Total is 100 million. So quite a big audience now. And let me do a little demo, if I may. Yeah, just I think it will illustrate really well the Ben's pitch afterwards on what we do at PhotoRoom AI. So this is PhotoRoom. This is where you land. Obviously, we are on iPhone, Android web, but we remove background, and you can automatically create an image. So that's the background removal segmentation algorithm. And now where we're really good, and it's the instant background, so generative AI features that you can see here. So I have my amazing sneakers, and actually PhotoRoom knows it's a pair of red and white sneakers. So we really understand the picture. That's why we can generate the best background for you, and that's really fast. It's like less than 1 second. And now, you can upscale, like choose any image. You can actually customize the description here. It's also like text-based model that will generate the best background for you. So it's a mix of text models and visual models that are making an amazing job here. And last part, you can actually get inspiration with images. So I can just drop, like, let's put that on a wooden floor, if I can do that. And I'll take my basketball floor and drop it here, and it'll just get inspired by the image I have here. And looks pretty good. Like the reflection, the light, the shadows, all inspired by the photo. And we also have a few other tools that are now in the platform, just like remove this messy part, super fast, and I'm good. Boom. Last part, and it's really unique, this one is if I pick a little red, purple, like pink background, we have a generative AI shadows, so studio-like shadows. The soft one is really good, but actually my favorite one is the other one, the floating shadows here. Makes your sneakers float. It's pretty cool. So here it is, and you can do batch. You can do many different things, but it shows you, for what Ben will do later, all the might and the power of the AI models in PhotoRoom. So more than 15 of them. And let's get back to, is that the PowerPoint? Yeah. So that's it. Like that's what PhotoRoom does, and I'm glad it offers that on iOS, Android web. We actually have the API that many big brands are using. We got Warner Bros. That work with us. Celency for a second-hand marketplace, so a lot of the circular economy is powered by PhotoRoom. A lot of the other platforms all over the world, some of the biggest marketplaces. And that's it. Very happy to host you here. It's first event, I told you. And last part, we're growing our audience, and we're also growing the team. So we're hiring many roles, and we love people building. We love artisans. That's the name of the original name of the company. And so come join us and enjoy the night and enjoy the talk from Ben.
Thanks. Right, thanks for the intro. So I'm not super used to this. It feels a bit like a wedding, and it's something that you get to practice a lot. So PhotoRoom, here we are. So I'll just talk about some of the features which are in the app, which you can see every day. It's not all of the AI that we do, and it's not super deep in the technical part, because I cannot put everything on the slide. I'm happy to field some questions afterwards. So if you know me, I'm a technical guy by heart, so you can ask anything. Next slide, please. So I'll just have a quick intro on why we're doing this, and I think it connects with the presentation from Matt, and we didn't. So it's not something that we practiced before, but it's just to emphasize the fact that we are a species which is focused on visual content, and that's why we want to build great tools for this, since we are a tool building species. And then I spend a bit more time on the AI actually, and I think that's why you are here. On 3 features which are in the app. Next slide, please. So it's kind of a repeat with what Matt was saying before, but it's outside of commerce, just that we do a lot of things through the eyes. It's like 2/3 of the brain electrical activity, 90% of the brain inputs. I won't go through all of the statistics, and I'm not sure that they are all super accurate actually, but the whole point is that we do a lot of things with images. And that's the motivation to invest in the field and to make it possible to create nice images. Next one, please. So since it's been a long time, and we're a species which builds tools for everything that we're not great at to begin with, and we're not all great at making nice pictures or nice paintings for what it's worth. So it's been a while, and there has been other tools before. So it's not a new topic per se. And only in the software part of the world, it has been something which has been prevalent since the 80s, that you had tools to help you create images. But I wanted to focus on a framework there, in that I think that all of the tools since the 80s and up to the 2020s share the same set of characteristics. One is that it would ask you for super precise inputs, so you would decide all of the transforms that you apply to the image. You would change the contrast, you would change the lighting, you would change the white balance, you may cut a part of the image and paste it somewhere else. But for all of this, it was a super precise question that the app was asking you to know, and how to get to the precise render that you had in mind. And something else was that all of these knobs that you had access to, they had been defined by somebody. So it was not machine learned, it was something where you had to be able to encode the effect of this contrast button and the effect of this change of lighting, of white balance and everything. So in the illustration on the right, it's actually taken from Florian, who is up there, or used to be up there. It's how it works in an engine like Photoshop or in PhotoRoom, in that all of your inputs are at the bottom, and then so it can be the contents of the different layers, or it can be a change that you request from the UI, and then you have a compute graph. So all of the changes that you apply to each of the part of the composite image that you get in the end are nodes in this graph, and you eventually get to the final image that you want in the end. And so all of this defines the render pipeline. If you're doing a game, then you don't expose all of the knobs, and the only input from the user is the point of view. But it's still a graph like this, basically. And it's a common, I think it's a common way of, so it's a common framework that we can use from Photoshop to game engines to a lot of other tools like Lightroom and others. Next slide, please. So yeah, then to formalize what we are doing at PhotoRoom in this framework is that we are trying to move the inputs from being entirely defined by the users to being defined by the AI, or this part of it, so that as a user you can ask for a high-level idea of what you want, but you're not supposed to specify super precisely what you want. And some of the transforms that you can apply are not something that you can hand code yourself. For instance, the estimation of the shadows in the example before is not something that you can code by hand. It's something that you can machine learn, because you have to have a machine which has a perception of depth from the picture, and which will understand from there how to draw the proper shadow. So we move both transforms in the nodes. If you can move to the next slide, please. Yeah, so it looks like this. So you don't have any precise knob that you can touch. And next slide again, please. Just it's the same point that yes, it's the same point again, that if you consider this compute graph, you either replace like whole nodes or series of nodes in this graph by AI black box, basically, or a box that you eventually know, or you address the inputs, or the fact that you are asking too much to the user. And why you are doing this is that if you ask a lot to the user, then you're restricting yourself to a population of experts. And if the only knobs that you have to create nice pictures are the ones that you can program, you're restricting yourself to things that you can humanly write, which we all know in XR is a subset of what we could do. Next slide, please. Thanks. Yeah, then so I'll just focus on three features which are in the app. It's not all of the AI which is in the app, but I thought that it was kind of a sequence, starting with the segmentation, since that's how the app was born in 2019, and then moving on to instant backgrounds, which was demoed by Matt before, and then suggested scenes, which touches a bit on NLP also, since I'm guessing that there are some NLP folks in the room. Next slide, please. Thanks. Yeah, so segmentation, I'm guessing that you already know this task. So the idea is, in our case, because there are different texts on this, the idea is to separate all of the pixels in two sets, so the ones that you want to keep, the ones that you want to discard. In reality, it's a bit more complicated than this, because some of so what you really want is the foreground, and some of the pixels will be halfway in between the foreground and the background, so you want to extract the foreground pixels out of that, so which has two benefits, in that you remove a lot of the super precise input that you expected from the users if you had to draw a mask, and you actually guess out of the blue what's the important part of the image that the user may be interested in. So again, that was the PhotoRoom starting point in 2019. I think that it was a good insight. and it proved successful. So the tech changed a lot since, but I think it's the same problem definition, and it's the same way we train the models. And as typical, I think in the ML space, once you define the model, so once you define the problem and you have some data, the actual implementation of the model is not the bottleneck. So the model has changed, but it's the same problem and it's the same definition. Thanks. So just to dive a little bit more, but I'm not saying much. So again, it's a mix of two tasks. If you think about it, you have to take into account the user and the scene. In that it's not as if you train a model to always segment the bottles, for instance, or the chairs or whatever. It's depending on the scene and on the context. You may be you have to guess that the user, in one case, may be interested in the chair, and in the other case, would be interested in the bottle. So it's a bit more complex than it looks from the outside. In that it's not that you can just have a data set with bottles and with the masks, and you train a model on this, and then it will work. And on top of this, you want to replace entirely the initial task of the user, which would draw a mask on a per pixel basis. So which means that you need to do predictions on a per pixel basis. So which is not that trivial in the ML space. So for instance, that discards out of the blue all of the annotations from Coco, if you think about it a bit more. So how to, I can just say that it's not just a U2Net. There was a blog post a couple of days ago which was discussing this, so that was kind of interesting. I think that you can get a long way with the U2Net, but it would be more specialized to a given topic. So, like, you can segment all of the bottles with the U2Net for sure. But if you want the scene understanding, that's you have to go a bit beyond this. You need a data set which is pixel perfect and which has this idea of saliency. That so in this context, it would be more like the important content of the image is this part, and it's not the same as in this other context, even if the semantics are the same. And I don't know of many public data sets which are doing this, which means that in this specific definition of the task, I don't think that the state of the art is actually published. I think that PhotoRoom may have it, and if it's not PhotoRoom, it's one of our own competitors, but it's certainly not in academia. Just touching upon some limitations. At PhotoRoom scale, you have a very big user distribution, so we need to understand what works for all of the users, and it may not be the same for people in the EU or in other parts of the world. You need to process at high res, and a lot of the papers in the CV space are at low resolution. That's not something which works for a product. If you return a 512 image or 256 image, that's not quite enough. I think the specialty of PhotoRoom is that we always work at low latency, so that I think that all of the calls we have now, and it was not the case just for a couple of months with the example that I will mention afterwards, but I think that all of the calls we have to our backend are all almost instant. So I won't give numbers, but it's so if you combine all of these needs, that's I think what makes some of the value of PhotoRoom there. Thanks. All right, so moving on and touching upon the Gen AI, which I think was the focus of this event. So I wanted to give some context with the text-to-image task, which is something that I'm sure you're all familiar with since last year. So in that case, as you know, the only input from the user is just the text to describe the scene that they want, and you just replace like this whole computer graph that I described before. The whole thing is replaced, and you have one input and you get the image back. So the task of the model there, if you think about it, is the lookup of the content. In that, if you ask for an astronaut on a horse, you need to know the concept of an astronaut, you need to know the concept of a horse, you need to know how to combine the concepts so that they make sense, even if it was not on the training set. The definition of the user intent is not always super precise, so you have to interpret some of it. So that's already quite a feat that it works so well. But then it has some limitations for PhotoRoom, so it's something that we offer on the web page, I think, but it's not in the app because it's not actually a great fit for the typical persona who's using PhotoRoom. And that for PhotoRoom, if you want to sell something, you often start with some visuals that you want to put forward, like a visual of an object, of something that you want to put forward, of a place or anything. but you start with something which is what you want to sell. And with this formula, since your input is only text, and the scope of the model is only that it can combine content which is in its own latent space. Like it's not trivial, or it doesn't work if you want to combine this with existing content. So what we set up to, yeah, thanks, next slide. On top of the previous scope, you add the task that you want to preserve as a part of the user content, and you want to integrate it with the scene, so that it has to match with the existing visual content that the model will add to the picture. All right, so it's more ambitious to some extent, but then you have a little less of the scene to imagine, so you can weigh this the way you want. Next slide, please. Thanks. So we did this in we shipped this in 2 steps, and the first step was not successful, but it was early, and we learned a lot out of it. So the first release was, the first stab at it was in November 2022. It was called Magic Studio, and it was based on fine-tuning. So the idea is, in that case, is that if you want the model to create a scene with the user content, then you have to teach the model the user content, and then it can create a new scene with this user content out of its memory, out of its new memory. So I think that was the first call on the first service that we had, which had a high latency, in that it was like 1 to 2 minutes, I think, at the time. And we optimized it a lot, but it was still 1 to 2 minutes. Yeah, if you can play the video, sorry. All right, thanks. So it's cleverly hidden in the video, but at some point you would get a mail, and that's how you get the image back. So that's not typical of the PhotoRoom flow, and it didn't work. So it was a good learning in that since we've always been trying to do something, or like to expose new features which are super short in terms of latency, or like super fast in terms of latency. And another issue that we had with this is that it was not perfect in preserving the user content, in that the model would show the shoe. In that case, I don't know if you can see this, but it would show the representation of the shoe that it could learn, and there were some small mistakes in there as well. Some of the textures, some of the fine details were not there, and some things the model could get wrong. Like we had an examples with people complaining about the number of stripes on their T-shirt, and the model got the T-shirt right, but it was not the right number of stripes. So we learned by shipping this that it was not good enough, and it was short-lived in the end, because we ramped it down like 2 months after or something like this. Next slide, please. So we had a second take at this, which is luckily still in the app, which we shipped in January 2023. So now it's a dedicated model. It's only inference, so it's a lot faster to compute. It's basically instant, or it's close to being instant. So we have a specific conditioning for this, since, as I was trying to explain before, it's not the text-to-image task. You have to change the model for that, and it's not completely off the shelf. And we have a specific in-house data set, and that's a thing that I will repeat, in that I think that in all of the serious AI companies, you always end up doing some work in the data set. So something that I want to mention here is that that it gets complicated with these features, in that from the outside it looks like it's one thing that you ask to the app, in that you start with some content and you want a nice picture out, but for real in the inside you call a lot of models for this, and every time one of the models fails, then there's no way the rest of the chain will work out, so you need the whole chain to be sharp, basically. So in that case, we segment first, and there are a bunch of models here. And then we do the core augmenting task at low resolution, and then we super raise this. So there are at least like 5 to 10 models in there. And it still needs to be instant, so you don't have a big budget. Thanks. So yeah, that's something that I should have started before, but it's a demo of how that looks in the app. You've already seen this, so that shouldn't be too new. So I think that it goes a bit fast, but something which is nice here, I think, is that the first scene, if you can post the video or in the end, sorry, Raphael. Yeah, just if you can post, thanks. Yeah, just that, so I went fast and I selected the first scene there, and it's a scene with cookies in the scene. And it's kind of nice because there are cookies on my mug. So it was on my mug yesterday. And that's not because we have a preset at the top for cookies in the scene. And that's not because I told the model to do so. So the answer to this is the next slide. In that with the previous take, you still have some user input in that like it can be a bit too big for the users in that you can generate anything. Like with the instant background, you can generate any scene. You can put your content in doing something abstract. You can put it on Mars. You can put it on a table. You can put it on a house. You can put it anywhere. And for a lot of users, so it's nice at first, but I think that for a lot of users who are looking for something which gives answers and which goes fast, it's a bit too much, and it's kind of a job half done in that we are not providing the users with all of the tools you need to go fast and have a nice and easy way to produce your high quality content. So I would try to tackle this is with the suggested scenes. So that's what I did in the video just before. So the idea there is that it's multimodal. So we move in between the text and the image space for this feature to work. We need to understand the user starting point, so which means that it will change for each of the pictures, and it's a way to personalize the experience and to personalize the generative AI to the actual starting point, also to the content of the user. And a nice thing with this also is that you can mix the use of some priors based on semantics and some user feedback, so that you can learn over time what the user like and you can improve your service. And the only user input in that case, except for providing the initial content, is that they just have to pick the choice that they like. So that's pretty fast. So two slides on how it works in practice. One is that you have to recognize the content of the image. And I wanted to emphasize some of the difference with academia here. Is that, so first, again, it has to be fast. So you know it now, but it's only one part of the whole graph. And the whole experience is below a second, I think. So this part, you cannot just put like a 5 or 10 billion text hour on this and just hope that it works. You have to have a description which emphasizes the visual cues. And in the example on the right, if the captioner doesn't mention that the chairs are blue and green and yellow, sorry, the chances are that the scene that will suggest will not match with these colors. So there's something a bit specific there that we want the model which recognizes the scene to know about. And finally, we want the model to be nice, and that's something that we discovered also in that if we output something, so the understanding of the model is visible to the user, and if we output something which is not very flattering, to many extent, like there are many ways not to be flattering, then it's a big issue. So you need a specific model for this, and again, you need a specific data set, and you need to own this in-house, basically. So that's an investment, but I think that it's worth it long term. I think that the future is multimodal, and the slide was prepared before the announcement from GPT-4 and Vision, but I think it's a good match. And I think that the future is also at things at text support, which goes beyond the English speakers, and that's something that we discovered with this project. That when we tried to translate this, then we discovered that there were a lot of extra steps to handle, and it's still not perfectly done. So it was a good learning. Thanks. Once you know about the scene, so about the initial content, then you can use another model, which is sec-to-sec. In that case, you can use semantic priors, so that's something that the model can learn in books, that coffee is in a coffee place or in a coffee kind of place. Basically, and you can use some user feedback in that you can learn over time that the user prefer this association or that this theme the model is good with. So that's what happens on the right. We recognize that it's a yellow sports car. As I mentioned before, the yellow part is important. Then the model is taught to know that it will look good on the road. They would be nice with the perspective. They would be nice with matching colors with the autumn, and so then you get boom, the scene which comes in the bottom. And for this, just a quick word that it was great with LLMs to prototype, in that the zero shot part is amazing there, but then the latency is way too big for this to be shippable. So in the end, you still have to own this part also. So, which means another data set and another model in-house and another set of optimization. Thanks. Last slide almost, just to mention that we're training a new model, so it's a bonus slide. So all of the examples on the right are from this new model. It's actually the second gen of this new model, so the first gen was not good enough, so we are still on it. So the goal here is to get to something which is more GPU friendly. Since we have a huge load on the backend, we generate millions of images a day, so that's a good motivation to optimize this. And to give an example, or to give a number, we can cram 40% more flops than Stable Diffusion v2 with the same latency, if you change a bit the architecture. We also believe that we have a specific use case since we try to keep things interactive, and that's not the case of some of the competitors we have in the field. And happy to discuss this, but training from scratch is not that bad. So it's supposed to be 50K from this blog post that you can link, so that you can follow from Mosaic ML. Actually, I think that it's probably 50K once it's super optimized and once you go in a straight line. So if you reproduce something which already exists, but then maybe that you shouldn't train to begin with. If you're not reproducing something which already exists, it's a bit more than this, but still it's doable. It's some work, and it's interesting, but it's doable. Thanks. Just closing thoughts. I'll insist on the fact that dataset building is underrated, so it's not part, I think, of the studies, and it's not valued enough, I think, in academia, since everyone tends to reuse ImageNet or Coco. But that's often not a good fit for companies. I think that latency is underrated. I think that you cannot expect everyone to use your app all the time if you make them wait all the time, like they won't wait for you all the time. They will just change to something else. Something that we don't always do, but I think that we learn a lot out of it is that if you ship, you learn. And you also learn with the shipping which go wrong, but then it's still a good learning instead of having something which you think is great but sitting on it. And we're hiring, and we have cool offsites with swimming pools. Happy to take questions. I don't know about the timing. I think I was way too long.
We can take a few questions. Who has a few questions for Ben or Matt?
Thanks for the demo. It's really very exciting. So I have a question related to OpenAI. I see a demo of latest OpenAI, and they have similar features like to get the foreground of the photos, and they can even like. I have impression that they have very similar features, and I can. I assume that like big companies, they will ship similar products in the coming months. So, so are you preparing for that, for the change on the market?
Yeah, so I think it's part of the motivation to train our own model and to get better at this. I think that if we stop doing something because there's an elephant in the room or there's a big player, then it's not good for innovation, and it's not actually the way it works. So I used to work at Facebook actually for a long while. With Guillaume, actually. And I think that there are so issues in big companies which mean that their product will probably be great, it will probably not be perfect, so there's probably a spot for us. So I'm not too worried, but it's a good pressure.
What are the main actions that you've taken to work on latency and reach this level of velocity?
First, it started before I joined. So I joined in 2022, and the team was already super good before. So I shouldn't take any credit there. And I cannot think of anything super specific that I did. I think that I should ask the team members who are still there of things that I do good or bad. But so what I can say is that from the is that we are a small team, but we are a team of experts, very senior people, and we own the whole stack. So everyone in the team can deploy models, and so there are people who are more knowledgeable in the deployment of the models. But one principle is that you own the whole flow from the initial training to the optimization of the model with some help. And it's often that we have to get back to the drawing board, and that the first version of the model which looked like it worked has actually a small issue, which means that it's not a great fit for prod. It's a bit too slow on some layer that we could replace by something else. So there's something that we didn't think well with how it work with the backend or with the apps. So I think that it makes it more complicated for newcomers and it slows us down a bit sometimes because we have a big stack. But I think that it's also what enables super fast experience in the end of the day. And it's kind of the way that Apple or Tesla works in that you invest a lot in owning the whole stack. And that's something that we do. And I'm guessing that is a good thing, or I'm hoping.
Yes, thank you for the presentation. I have a question. So when you say you own your own stack, do you still rely, especially for image, the last part of the flow for the image generation, you still rely on things like Stable Diffusion, or have you created everything on your own?
No. So it's not everything, and there are a lot of great open source parts, for instance. No, but I meant that. So it's. I don't think that we own 100% of all of the layers, but we own a lot of the layers. So like from the training to the evaluation, to the building of the data set, to the compilation of the models which go into production, which are not PyTorch. So it's. I don't think that we can claim that we own fully any of these steps, basically. And there are a lot of great tools here that we use, and there are a lot of parts of models that we use. But it's more that we have our hands and we have a good understanding, I think, in a lot of these layers, and I don't think that it's that typical. So it's not the case if you reuse a dataset which exists out of the blue, then it means that out of the box, then it means that there's a ceiling to what you can do with this. Or if you don't optimize your models for production, then it means that they will, if you have a bottleneck on the latency that the user perceives, it means that there's a limit on the number of flops that you can put into the model, and which then means that there's a limit on the quality. So yeah, I think that it all goes together, basically. That's what I meant.
Maybe just one or a couple of more questions if some of you in here have more questions.
Hi, thank you. I wanted to know if all the calculations are done on your server through an API, or if you manage to have some calculations on the user's machine.
Yeah, it's a good question. We have a mix of both, but to be frank, we have mostly on the backend, in the cloud. Like we don't have a lot of on device, and I think that it's true of a lot of the players in the field in that it's if you have 50 million people on Android using your app, then you have not 15 million different smartphones, but you have at least 10,000 different smartphones, and it gets super hard to optimize the whole stack for this. So at some point, it's simpler to move it to your own backend and own this part.
Sorry, last question.
Thank you. For example, for the last model about image generation, how many people are working for how long, to get this? Is it a 5%, 6 months work, or?
You can ask Antoine, who is on the seat just close to you. He's the one who did the biggest part of the work there. No, we are not a lot of people. We are 7 in the team with 2 interns. I don't know if I can see David here. Yes, so 7 in the team plus me. So and we cover quite some ground. So which means that we don't have 5 people on Gen AI. We have like 1.5 or 2 people. On the Gen AI, so we have other aspects than this core than this core model. So it would be more like 3 people maybe on this.
All right, so thanks, Ben. Thank you very much. And so next we welcome Guillaume.
So hi everyone, my name is Guillaume, and today I'm going to talk about LLaMA. So the first language model that was released by Meta in February 2023. So I'm going to very briefly summarize the motivation and the background at the time, so why we built LLaMA. Then I will talk a bit about some technical details like the training data we used, the architecture of the model, quickly talk about how we evaluate this model, then present some results, draw some conclusion, and then very briefly talk about Mistral, which is now our company. Yeah, so the project started in August 2022 at Meta. It was at the beginning a team of 5 people working from different projects. And the reason that we basically decided to work together on LLaMA is because it's very difficult today if you work in natural language processing to actually work without LLM. So it doesn't matter what you do, whether it is machine translation, summarization, any task typically. And in our case, we were working on trying to solve mathematical problems using deep learning. And we were doing this, it's essentially an NLP problem, the way you frame it. And it's very difficult to do this without LLMs. So we basically decided that we had to train one, because at the time there were no really good open source models. There were some, but they were very, very far from the model of OpenAI. So we played a bit with the codex, the model from OpenAI. There was an API, but it was very expensive. And it's also a model we wanted to actually be able to query much faster than what we could do with the API. So we thought that if we want to remain competitive, we need to actually build these models. So the first question that you have to answer when you build such model is basically how large is going to be your model, what is the size. So typically GPT-3 was a 175 billion parameter model. Then Gopher by DeepMind was 280 billion. Then there was this model by Google, Lambda, that was a bit smaller than GPT-3. And then there was this huge model released by NVIDIA, so MT and NLG. And then there was this very interesting paper by DeepMind, Chinchilla, on what they saw. So what they showed is that you can actually train state-of-the-art models that are actually much smaller than what people typically use in LLMs. In particular, they showed that with 70 billion parameters, you can actually have a state-of-the-art model. And what they did is that they actually, the difference was not the architecture or anything. There were some small differences, but mainly it's simply that they trained the model 5 times longer than the predecessors. So typically, GPT-3 was trained on 300 billion parameters, tokens. And the Chinchilla was trained on 1.4 trillion tokens. So the question that was addressed in the paper is typically the following. So if you have a compute budget, so for instance, let's say you have 1,000 GPU for 1 month, and you want to train the best possible model, so what should you do? Should you train a 100 billion parameter model on this many tokens? Or maybe should you train a twice smaller model but on twice as many tokens? Or do you want to train a larger model on less tokens? So it was essentially answering this question and telling you what is the ideal number of tokens for each model size. And typically the previous ones were clearly undertrained, and it was showing that you have to train it much more than what people typically do. So there are many benefits when you train smaller models. So simply it's easier, you have less instabilities, the model doesn't explode. In terms of engineering, you don't have to, you don't need as many GPUs. It's faster to train. Inference is also much faster. You can make inference on just one node or potentially just a few GPUs. So everything is, life is just easier. And then if you want to use it for research, you can generate sentences and decode sequences much faster. So we decided that we will actually train several models. So 4 models, so the 7, 13, 33, and 65 billion parameter models that we at the end released. So the 2 first one will be trained on 1 trillion tokens, and the 2 largest one on 1.4 trillion tokens. So when I talk about tokens, so very briefly, so a token is essentially just a word. The idea is that if you have a sentence, you want to cut it into some sub-words that you can feed into your model. On the tokens, there are essentially some sub-word units. So typically if you have a sentence like how are you, so that these words are common, so each word will actually have a token. If you have some less common words, like the second example, here these words are not very common in your training set, so you will actually split them into subwords. And the very nice thing about this is that you can actually tokenize any basically sequence of text, even if it's code, for instance, you can actually tokenize this using the same vocabulary. And you don't have this issue of unknown words, so whenever you have some word you have never seen before, it's simple, you just cut it into smaller pieces recursively until all the subwords you have, up to the character level, are known. So when this paper came out, the paper that presented this, it was kind of a revolution because it basically solved this question of what to do with unknown words in basically just one trick. So it was actually extremely convenient, and today everybody is using this. So for the data, so as I said, we need to find 1.4 trillion tokens, so it's not easy to find. So to put this number in perspective, you can look at Wikipedia, for instance. So in English on Wikipedia, you have 6 billion tokens. You have a bit less than half than this in French, so a bit less than 3 billion tokens. And if you look at the top 20 languages, so the Wikipedia languages with the highest corpora, for all the alphabets that are either in Latin or Cyrillic, so Latin and Cyrillic alphabets, you have 27 billion tokens. So at the end, you need to find 50 times more tokens than this, and they are not one. You have a few others. One is archive. So on archive, you have 2 million publications, so it's 35 billion tokens. You have Stack Exchange, which is a collection of websites. Stack Overflow is the most famous one, also the largest among all of these. It's 26 billion tokens. On GitHub, you have a lot of data on GitHub, between 500 billion and 1 trillion token based on how much you decide to be aggressive on your data cleaning and data processing, and if you want to remove the files that do not seem interesting, or based on the extensions also you want to consider. But the largest one is by far Command Crawl. So Command Crawl at the end was more than 80% of our data. So Command Crawl is essentially 240 billion pages from the internet that have been collected over more than 15 years, 16 years. And interestingly, what we found is that the internet over this last 16 years is actually much, much larger than if you were to just crawl internet today. We thought that just if you were to crawl the internet today, most websites will be there, but actually there are more websites today than before as well. But actually, you will actually have way less data than if you use this historical data collected over 16 years. So it's a huge data set. The raw data is, I think, maybe 6 petabytes, so it's really huge. So it's huge, but it's also, as a consequence, not easy to process, and it's very noisy. You have a lot of noise, a lot of data you don't want to use on the internet to train your model. On each web page is provided in 2 formats, so either HTML, so the raw HTML, the same thing you have when you are on your browser and look at the source of the page. And you have also a processed version that they give, which is, they extract the text of the page, but it's typically not really well done because you have still all the menu, all the the things about the banners, the cookies, warnings, everything, the copyrights at the bottom. So all this information is not useful to train your model, but it's still there, so you want to remove this. But it's easier to do it if you have the source, because typically if you have the HTML page, you can, people will use this navigation HTML5 tag, so it's easy to remove the noise. So we actually reprocessed everything from the raw HTML. So then there are many things you want to do. First of all, you want to filter the URLs. For instance, remove the websites that are potentially harmful, that have either some hatred content or porn content as well. You also want to filter the languages. So in particular, in our case, we just wanted the English content. Then you want to remove the duplicates. There are many web pages that appear hundreds of times or potentially thousands of times, even more. You want to remove at the line level the lines that appear multiple times. So yeah. Plus the noise removal. And at the end, we had some quality filters. So the point of the quality filter is to remove the pages that, even if they look very clean and properly formatted and everything, there is actually not much interesting content on it. So you can train some classifiers on what you think is interesting. For instance, let's say Wikipedia, and you can say that some negative samples are some random pages, and then you have a classifier that will say this page looks good, this one doesn't, and you can actually filter out. Actually, at the end, I think it's 90% of the pages that we remove. And yeah, so if you do this, at the end you have around, that depends how aggressive you are on your filter again, but you can have trillions of tokens, so there is really no limit. So this was the final data mixture we had for LLaMA 1. So the command crawl, we had 2 versions. So one is CCNet that was processed by people at Meta a bit before us, and then there was C4, which was the same version but by Google. So we used the 2 because adding C4 for us was one way to have more tokens, because it was difficult to find this 1.4 trillion token. At the end, I think basically all our data together was pretty much the final size, so we didn't have a lot of extra, except for the code, but we didn't want to use much more code than what people typically used to train these models. On the last 2 that I didn't mention were the books. So we use books from 2 collections. One was Gutenberg, so it's a collection of books from the public domain, and one was Books 3, which is a data set of books that was released by some other company. So interestingly, there are very few differences between the final architecture of model today, the best model open source you can find, on the original version published in 2017. So even though there has been many, probably hundreds of variations of transformer proposed, really there is nothing that really stands out, except for us, what we found to be actually interesting was this rotary embeddings, which is an improvement over the initial positional embeddings of the Vasmani paper, plus the strict glue activation, which is a replacement for the ReLU in the Eurofit forward activation. So yeah. Plus, we initialize the weight differently, doing something similar to Palm, a paper by Google before. And yeah. So for all the models, as the model was becoming bigger, I mean, we basically try to increase both the dimensionality and the number of layers as we wanted the model to be larger. Yeah, and for the largest model, we took the exact same architecture as the Chinchilla model of DeepMind. It was supposed to be 70, but for us it was 65 billion. I don't know, they found some extra tokens, some parameters somewhere, but yeah. So these are the training curves we obtained. Surprisingly, and it was a nice surprise to us, but there were very few instabilities. We were afraid that, we had heard stories about how horrible it is to train this model, like everything crashes, the model, the loss goes to infinity, you have some nans everywhere, but it was actually, it actually went very, there was no issue. The loss actually were pretty smooth, as you can see. The LLaMA 7B was trained on 500 GPU for 1 week. On the largest model, the LLaMA 65B was trained on, so theoretically it should have been 3 weeks. If with the code base we had, it would have been 3 weeks on 2000 A100s. But there were a lot of hardware failures. So that's kind of an issue with this GPU, is that even though they are fast, they are very unstable. Sometimes they crash, you don't really know why. Sometimes you have some communications that doesn't go through. You have the model that just stops training, it doesn't tell you why. I think the worst issue we had was that sometimes when you, some GPU, and when they do some matrix multiplications, they will actually give you some corrupted outputs. So they will just multiply 2 matrices, give you something wrong, and silently, and you don't even know why. It doesn't say any warnings, just it's wrong. And then you actually see some extremely, you see some spikes. So this is actually the only times we saw some loss diverging. But then when this happens, it means the GPU has an issue, and then the loss goes wild very, very quickly, so it's easy to spot. Sometimes it's a bit more difficult to spot the GPU that was responsible. If you have 2000 GPU, you have to figure out which one was bad and then start on another one. But that was, I think, the most difficult thing of these trainings, to actually figure out what was the defective hardware. So it should have been 3 weeks, but then it was 4 weeks because of these reasons. Yeah. Yeah, and also some other thing we didn't mention in the paper or anywhere is that to actually accelerate the training, we had some tricks where we manually recomputed the gradients of the backward function of the training. And the idea was that we wanted to make some optimization, so we wanted to overlap as much as possible the communication between the GPU. So typically what you do is that if you have 65 billion parameter, it doesn't fit on one GPU. So what you do is that you cut your model into shards. So if you have 1,000 GPU, you have 1,000 pieces. Each GPU will actually take care of 1,000th of the model. And what you do is that whenever you forward a sequence, each layer will actually gather the rest of the parameter of the layer all across the network. So every time you go through a layer, each GPU will fetch the remaining parameter over the 1,000th GPU, compute the next layer, then forget the weights. So you do this to actually be able to train these models even though they don't fit on one GPU. So to actually make this fast, what you want to do is overlap as much as possible the computation of the layers plus this gathering of the parameters of the next layer you are about to compute. So to do this, we had to manually re-implement a couple of things, and we made a mistake in the gradient computation. It was a false gradient, so it didn't impact the first runs. A priori not much. But for the 65 billion parameter model, it actually did. So I think that at around, 1,000 billion, so 1 trillion token, the red curve initially was actually crossing the green curve. And we knew there was something wrong. And it was happening after, I think, 3 weeks of training during Christmas. It was horrible. So I think we found this bug. We are pretty lucky to find it. We found it, we fixed it, we restarted. We were not sure if it was actually the reason it diverged, but actually it was. And then after we restarted it, it actually worked well. So maybe, I think related to what Benjamin said before, when people estimate the price of the training of these models, they usually don't take into account that it actually takes a lot of time to get there. We actually worked, I think, 4 months before we started these final trainings. So even though the final model is maybe not so expensive, all the way to get there actually is actually much more expensive. So for the evaluation, it's actually a bit more complicated than before. Before it was very simple. You had for each task a data set with a training valid on test split. So you'll train on the training set, report the performance of the test split. Now it's a bit more complicated. I mean, a few years ago it was still okay. People, for instance, when they were training models like BERT, Roberta, XLM, what they will do is that they will train their model on their data set. Then you have some very common benchmarks that they will use. They will fine-tune their model and their benchmarks and report the accuracy on this. But it was still a bit noisy because sometimes you will do a better job at fine-tuning these benchmarks. So you might say your model is better initially, but maybe it's because you fine-tune it better than another one. So it started becoming complicated. Oh no, it's really a mess because nobody's using the same data. Nobody wants to say what data they use. The fine-tuning is expensive, so you can't do that anymore. So what we do now is actually, I think, not so bad. We use this zero-shot evaluation metrics. So here is an example of one of them. So MMLU, it's a famous task. The idea is that you have a lot of questions split into 57 categories about mathematics, history, computer science, etc. And they're pretty difficult. So here is an example. I mean, you have some question about medicine, I guess. And you give this to your model, and you ask it to predict A, B, C, and D. And you look whether the model is accurate. So if you reply randomly, you have 25% chance of being successful. The average human is 34%. And actually, it's not easy to get a model that does better than 25%. And yeah, so here are the results we got at the end. So I'm not going to go into the details of all these tasks, but they are all the same thing. It's just a question. Sometimes it's sentiment classification. You have like a sentence, you see what the model wants to put afterwards. I mean, they are all the same thing, zero shot. And here what was interesting is that LLaMA, so here are the results of LLaMA, it was actually better than all of this other model, not everywhere, but on this common sense reasoning task it was actually really good, even sometimes better than the 500 billion parameter model of Palm of Google. Yeah, so something which is kind of controversy today is, can you trust this benchmark? If a model has a good accuracy on some benchmark doesn't mean it's good. And the problem is that these benchmarks are actually very sensitive. So for instance, before I was showing you a question and the answer was D, but there are many, what you try to do is see whether the model wants to predict A or predict B, C or D, but maybe the model wants to predict 4 minutes, that was the solution to the question, or maybe it wants to predict answer colon D or answer colon 4 minutes. And based on what you evaluate, you can actually get some very significant differences in performance. You can get sometimes like, I don't know, 5%, but 5% is a lot because if you look at, 5% is typically, I mean, if you look at some metrics like, I don't know, the last column, okay, maybe not this one, but okay, the middle one, LLaMA swag, 3% is typically the difference you get between a LLaMA and the LLaMA of the next size. So if your metrics are noisy by 3%, and that this is the difference you have between two models that are twice larger, I mean, one being twice larger than the other, it's actually an issue. So to address this issue, I mean, now what we do is that we have some common repositories, some common GitHub that people use, and as long as you use the same code base to evaluate two models, it's usually fine. But it's not always fine. Typically, when we released LLaMA, people didn't believe the results for many weeks. It was annoying because when people implemented, actually plugged LLaMA into these public benchmarks that there was some issue in the in the way the data was tokenized, and because of this, the results were off by 10%. So it took people a while to figure it out. And the issue is that it's very difficult to find these bugs. Sometimes it's always some silent bugs. So to address, to make these benchmarks a bit more stable, what we often do is that we use this few-shot evaluation. So few-shot is the same thing, same as before, except that you don't directly give the question and let the model predict the answer, but you give, if it's 5-shot, so for 5-shot evaluation, you give 5 examples of question 1, answer 1, question 2, answer 2, 5 times, and then you give your new question and you see whether your model predicts a good answer. And if you do this, so not only it improves the performance of your model, because you tell your model, you give it some examples of what you expect from it, so it understands the task, so then it actually does a better job at doing your task. And so the performance improves, So as you can see on this example, you go from 65 to 70 for the 33B LLaMA, but it's also much more stable. Yeah. So here some quick curves of the evaluation of the performance of the 4 LLaMA over time. So the violet curve is actually the performance of Chinchilla. And you can see the good metrics and the bad metrics. So the good metrics are the ones where when the model trains more, the accuracy increases, which is expected. There are also the metrics where, I mean, you expect the LLaMA which is larger to be better than the LLaMA which is smaller. So the metrics on the top are good. We usually like these ones. The Sika one at the bottom left is usually, you see that if you evaluate your model with that, it's not a good way to evaluate your model because you clearly have models that are better. The red one is supposed to be better, but it's not obvious if you report results on these metrics. So that's why you can't. You need to have several metrics. In practice, I think in LLaMA we had like 20 or something. So yeah, so just to conclude, so some of the message some of the things we found and discovered when we worked on this project is that first of all, you should train much more than what is suggested by the Chinchilla paper. I think many people didn't understand what was in this paper, and now there is even this concept of a Chinchilla trap. The idea is that you should train a model of this size on this number of tokens. So then even people, at some point, were releasing some new models saying this is Chinchilla optimal, but it's actually not a good thing to do. If you give model to people, you don't want your model to be Chinchilla optimal, because if it's Chinchilla optimal, it means that you actually stop the training when the loss was going down. And if the loss is going down, you don't want to stop the training, so you want to keep training. The Chinchilla paper was overlooking the inference cost. It was just replying to the question on how many tokens do you want to use, assuming you have a fixed computational budget. But of course, at the end, you want to deploy your model. So if you want to deploy your model, you have to think about that as well. So you probably want to train longer, even if it's not the best, but then inference will be cheaper. The other message was that you can train state-of-the-art models with publicly available data. You don't need to have some data, like some proprietary data set. We don't know what OpenAI is using or anything, but you don't need to have this ultra-clean data from we don't know where. If you just use internet, command crawl, that's good enough. I mean, you can get some very good model at least with that. And yeah, and if you overtrain, if you train longer, a 13 billion parameter model, LLaMA 13B, you actually can outperform even the original GPT-3 that was more than 10 times larger. And overall, even though we are a bit afraid of this project, it was actually very simple conceptually. There were a lot of engineering challenges and issues and annoying things like fixing the GPU crashes and everything. But overall, there were no secret sauce or anything really. At the end, the architecture we have is almost the same one from 2017. It was just a question of, I think, doing things properly and cleaning your data well. And but no real magic. So yeah, just wanted to thank the people, the other first author of the paper, so Hugo, Thibault, Gauthier and Edouard. And so very quickly, LLaMA 2. So LLaMA 2 was the same data set on architecture. It was trained longer on 2 trillion tokens. And what was interesting to see is that even if you train longer, you see that the performance still improves, which means that we train on 1.4, the LLaMA 1, 1.4 trillion tokens. But even at 1.4 trillion, you see that the model is not saturated, because even at 2 trillion, it's actually even better than the 1.4. So now the question that I think everybody was asking after LLaMA 2 was, how long can you go? Is it better after 4 trillion, 6 trillion tokens? How far can you push these numbers of these small models? And, yeah. So a last very quick slide about Mistral. So we created Mistral in June 2023. What we do is that we train a large language model for businesses. We want these models to be small and efficient in the same spirit of LLaMA, because when you deploy model, you want them to be very fast. We have a focus on open source, and we released our first model today. So it was completely related to this event. I think it was a coincidence. We planned this. I think only 2 weeks ago. So just to show some numbers of Mistral 7B. So Mistral 7B is actually much better than LLaMA 2 13B. So here are some results on some benchmarks. It's actually the first model that exceeds 60% accuracy on MMLU, the benchmark I was showing just above. And yeah, it's also released under the Apache 2 license, which is a more flexible license than the one used by Meta for the LLaMA model. and it handles much longer sequences, up to 8K tokens. And you have, we also added these new kernels for sliding attention window. So there are some details about this on the blog post we released. But the idea is that you can actually take into input sequences with up to a theoretical 128,000 tokens. So yeah, just some other results on different kind of categories. So there is MMLU, this science on kind of tasks, the knowledge, reasoning, and compression benchmarks. And you can see that the Mistral 7B is way above the LLaMA 2 13B, and it's also above the LLaMA 1 34B on many kind of categories. We did not have numbers for the LLaMA 2 30B because Meta did not release it, so we were not able to evaluate it with our benchmark. Yeah. Thank you.
Questions for Guillaume?
Thanks for the presentation. I have a question for the non-deterministic output for LLM. So we see that maybe it's by design. So even we ask the same question with same prompt, and we can get different results. And this is by design, and this can bring risks in business. So my question is this part of the measurement of LLM? And do you think it's a risk that we need to handle in the near future?
You mean, is it a risk, like if we put a model like this in production or something?
Yep.
Yeah. I'm not sure. I mean, I think it depends on what you want to do. Typically, this question of determinism is also something we have in the evaluation. So typically, when you evaluate your model based on the task you use, you can actually make it deterministic. You can just actually make a greedy decoding, which is what we use for actually most of these benchmarks. Sometimes you want your model to generate many solutions because you are in a setup where you can verify if your solution is correct or not. For instance, I mean, there are some tasks like this where you have some unit tests, you just need to generate one solution that passes them. So you can actually sample many of them, and you actually, maybe like 100, and you just can actually score 1 point if you actually have one solution that passes this test. But otherwise, I think it really depends on the kind of application. I mean, I think if you are doing code generation, you probably want to actually sample many solutions if you think the first one is not satisfactory. If you're in a setup where you want the output to be very reliable, you probably want to have a temperature of 0, so to be greedy, to actually output the model most confident answer. So I think it really depends on the kind of task you are doing. I think if you want to use a model to get some creative content generation, to write like an article or rewrite a sentence, rephrase something, then you actually want to have a high temperature, generate different outputs. But for now, in terms of, I think safety doesn't, you always have to manually inspect whatever you are generating. There is no, I think, real solution to address this for now.
What are the most exciting area of research, according to you, to keep improving this LLM currently? And maybe more specifically, what do you think about the mixture of experts approach that seems to be...
I'm sorry, who is talking? I can see.
Sorry, okay. It's me.
Sorry.
That seems to be implemented in GPT-4.
Sorry, I did not hear the second question.
Okay, what do you think about the mixture of experts architecture or approach that seems to be implemented?
So for me, the promising directions, I think, are around this idea of... so for now, I think a problem with current models is that if you, let's say you have a 7B model, it's extremely fast at decoding, much faster than a, let's say, 200 billion parameter model. But the problem is that you cannot... if you ask a complicated question to your model, it will generate an answer. If it's wrong, there is pretty much nothing you can do about it. And I think it's unfortunate you cannot tell your model, here is a question, you can think about it for 1 hour, you have an arbitrary amount of time, so think about it and output me the solution you think after 1 hour. I think it's a little bit like if you give a very complicated math problem to a student, maybe you will not find it on the spot, but maybe if you give them enough time, after 1 hour they will find a solution. And you don't have this idea at all in current LLMs. They just spit a solution, and if it's wrong, I mean, that's wrong. And so there have been some attempts, I think, to address these problems. For instance, the universal transformer, I think, is really nice. The idea is that you have an input, you forward it to your transformer, and then you have a classifier that says, I am ready to answer, so I'm going to give you a solution. Or it can tell you, I'm not ready, I need to think more. So if it needs to think more, it takes the output, reprocess it, and you can actually do this an arbitrary number of times. And I think it's very interesting because it basically means that, it doesn't make sense that if you ask a question to a model, it outputs a solution with the same reflection time, with the same thinking time, regardless of the difficulty of the question. If you ask a model what is 2 + 2, or can you solve this complex math problem, it will take the same time to output the solution, and I think it's not something you wish. And for the mixture of experts, I think it's something which is particularly useful if you put something into production. So these models are much more expensive to train, because typically if you have 16 experts, you have 16 more blocks of matrices to learn. So it takes longer to train. But the nice thing is that at inference, you actually have much more parameter available. So it's your model has much more knowledge. And something that also people don't realize with the mixture of experts, but which is actually really nice, is that in text, unlike in maybe some other domains, even though you only use one expert at each token, so you generate one word, you use one expert, then at the next word you might use another expert. So it means that even if you have 16 experts, on your model is, let's say, 16 experts of size 100 billion, you will use one expert per token. So if you generate a sequence, you might actually use all of them. So you might use maybe your 1.6 trillion parameter model, parameters, if you have 16 experts of 100 billion. So it's really nice. Yeah, it's just more difficult to train, more difficult to engineer. The problem, I think, the challenges we had here were difficult, but they would have been worse with MOE. You have to really program things differently. And, yeah.
Thank you for the presentation. My question is, in LLaMA benchmark, there was a column that is entitled math. What does it mean? Like, is it related to the ability of the LLM to solve math problems, and can we do better?
So I didn't get the question. Sorry.
Like there was a column in the LLaMA benchmark that is entitled math. What does it mean? Like, how can we measure this performance?
So for math, there are a few different data sets of evaluations. The most common is a data set that's just called math, actually. And the idea is that you have a bunch of questions that are actually pretty difficult. Not IMO level, but still difficult. And these are questions, all of the form, it's not things like prove that this is true, or prove this, or prove that. It's questions of the form, compute the area of this, compute the angle between these two lines. It's questions where you have like typically a digit, or like an analytical, you have a solution which is like a formula. And what you do is that you basically ask your model the question, you make it generate a solution, and you see whether the model actually just outputs the solution. This is tasks that you do in a few shot tasks. So in a few shot you can give some example of input-output. On the output, the solution is always put in a box. So in the LaTeX, the LaTeX M box that says this is a solution. So then you basically tell the model to generate a solution, and then to highlight, to put in a box its solution. So you generate a solution, you look at it, and you compare it with the goal truth, and that's it. So what you can do is, what we do for this benchmark is that we sample typically, I think, 100 solutions, and you see if one of them is a sentence where the model generates something, and that puts like the solution, the good solution, in one box. It's totally possible that you have some false positive. So for instance, the models kind of randomly figure out the solution. It happens, but that's how we do it. In practice, if the model, any model can do this, and it still remains like a good way to compare models. It's maybe not a perfect benchmark, but if you want to compare models together, it's good.
I think we have a few more questions that we'll try to take, but then we also have our startups. So I've seen you.
Thank you for the presentation. I read a paper that there will be somehow lack of data available for training. Did you try to generate with LLM some data to train other LLM?
I think using So this will work only if you have a model, if you want to train a model smaller than the one that generates things. Because if you have a small model and want to generate something, it will be something lower quality than what your higher model can learn. But if you actually are in this setup, what people typically do is distillation. So what you do is that you take your large model, and then when you train your small model, you don't train it to predict the next word, but the probability distribution of the next word according to your larger model. And it actually provides more information. It's a less sparse reward than, you don't say just predict this next word, you say predict this probability for this one, this probability for this one. So you actually learn faster and better. So that's typically what we do. Otherwise, using other models to train, synthetic data to train other models is something we do at fine-tuning. So when you do this RLHF kind of thing, supervised fine-tuning, you do that. What you do is that, for instance, you ask a question to your model. You can tell your model to generate, let's say, 10 answers. Then you will ask a human to select which answer is the best among the 10, and then you can actually fine-tune your same model on this selected answer. So that's how you actually train on your synthetic data, but that's only for fine-tuning.
Yes, thank you, Guillaume. I have a question about the data set as well. You've probably said it, but I didn't understand when you said LLaMA 1 was trained with 1 trillion tokens and GPT-3 with 3 billion tokens, if I remember well. The 1 trillion, is this because you had your data set was 3 times bigger, or just because you did more epochs on it for the training part? And I have a second question about the datasets in the future, because the datasets will be in the future, for future models, they will gather data that will be crawled on the web. An increasing part of this data will be generated by AI, by ChatGPT and Mistral AI, 7B, and so on. And I've read a paper about the risk of the performance of future model collapsing if they train too much on less diverse data created by generative AI models. What do you think about this risk of collapse, and what is the need of fresh human data?
Yeah, I think, so for the first question, we did, so it's true that there are some data which is higher quality than other. Typically Wikipedia is the highest quality. Archive is also good, same for Stack Exchange. So typically what we do is that we do multiple epochs on this. So even if Wikipedia is, 30 billion token, we will maybe train it 3 times on it and have 100 billion token. So we upsample what we think is high quality. So at the end of the day, we didn't have to do more than 1 epoch on Common Crawl because it was large enough. But yeah, the strategy is you don't concatenate everything and then shuffle and do 1 pass and repeat if you need more tokens. You actually upsample. You generally just have you decide some proportion. So for instance, 4% Wikipedia, 3% archive, 4% GitHub, and then you train with this proportion. And it can be that maybe you will do 1-2 epochs on some data sets, but that's you don't think, I think, as much in terms of epochs as in terms of data distribution. In particular for this, we actually just took the data distribution provided by Chinchilla. We wanted to be as close as possible to what was the state of the art at the time. For the second question, I think it's really an issue indeed that probably in the future most of the internet content will be generated by these large language models, and if you have a text you don't even know where it comes from. And I think what's even more annoying is that OpenAI probably will know, because you can easily watermark your generations, and if it's watermarked you can actually identify this is something I generated or not, but some other people will not be able to do this. So we don't know yet, I think, if it's an issue. But if it is, some companies will know what to exclude and some will not know, so it's probably, it might be an issue. But I think I'm not too worried necessarily, because in a way this data selection is kind of a RLHF already, in the sense that you take your whatever model you have, you ask a question, let's say you make your model generate an article. I think it's unlikely people will just copy-paste it on their webpage. They will modify it, improve it. If it's perfect, they might just copy-paste it, but then it means it's perfect, so why not just train on this? So I think my hope at least is that data that will be coming from LLMs has been manually curated and selected by humans beforehand, so it should be high quality, and I think it's safe to train on that, hopefully.
Thank you, Guillaume. I had a question on the performance of LLaMA. So you said you were using, like, architectures have not changed that much since 2017, and you were still able to beat Palm with one order of magnitude less, 65 against 480 billion parameters there. So I was wondering, what do you believe was the key there to the success? Was it the data set? Was it the tokens? Was it the training time or schedule?
I can't know for sure, but I think it's mostly the data set. So Palm is so Google is never very clear about the data they use. And I think for Palm, 50% of the data set was composed of one data source called social conversation, but nobody knows what it is. And I suspect it was not very high quality. You might want to train on content with more information, maybe more documents that will help you to do some reasoning, mathematical reasoning. Maybe on social conversation, you don't touch a lot of these science kind of topics, which are reflected in the benchmarks. So I think that's mostly the data set. I forgot how much they trained. I don't know if they released this information, but I suspect a model this large, they obviously did not train as long as LLaMA. You cannot train a 500 billion parameter model this long. Maybe they can now, but at the time they probably didn't do it. And yeah, I think it was mostly that. In terms of architecture, there were a few differences between what we did on Palm, but I don't believe it could have been the explanation.
All right, so Guillaume will be here at least for a short while at the cocktail, so you can ask him your remaining questions. I've seen a few, so thanks a lot. Thanks, Guillaume, for your presentation.
Hello, so I'm Sami, I'm the CEO of Stelia. So we are building a tutor to help to boost access to knowledge for learners from schools, higher ed, and corporate. And so for that we are a 27 people team, one third of it being data scientists. And we explore and combine and fine-tune AI models to make the most of the knowledge. So we deliver such assistance, so with a rich answer, so not only a generative answer to a question, but also the source it's relying on, the related concepts and related excerpts. So we worked on videos as well with speech-to-text. We work on knowledge graph, and so we provide a multimodal answer. So for that, we have a rich pipeline. So we ingest documents from our customers. So we focus solely on their knowledge, documents, audios, videos, APIs, and so on. And we have several steps to extract the knowledge from it. So segment it, categorize it to identify the most relevant knowledge. And that's it.
Yes.
Yes.
Hello, everybody. We are Gemini, the AI copilot for next generation law firms. I'm Raphaël Laroche, the CEO of Gemini. I'm graduated from edX, so I'm the business guy of the team. I'm the former co-founder of Monpostulant.fr, which is a French legal tech gathering more than 7% of the French lawyers on the platform. And this is Steph.
And I'm Stéphane Berreux. I'm a Polytechnique student, X17. I did a specialization in data science, and then I joined Entrepreneur First, where we met.
So what we do at Gemini, we have a vertical approach on Gen AI applied to the legal industry. We are providing law firms with an AI copilot, enhancing their capabilities on all the low value-added parts of their work, namely 3 types of tasks, which are the legal answers, So you can think about that as a legal ChatGPT, the document review, and the legal doc drafts powered by AI.
So creating such an assistant implied a lot of technical changes, from the knowledge representation up to the reasoning of the large language models that I'd be happy to discuss further with you at our stand later.
We are closing our first round of financing, so we are recruiting a lot. We'll be right after at the stands, so don't hesitate to join us for a few questions. Thank you.
Yep. Hi, I'm Henry. I'm the CEO and co-founder of Newton. And
I'm Julien, the CTO of Newton.
And we didn't went to Polytechnique. Newton, at Newton, we're building the marketing AI API to produce ultra-personalized branded content. So we're helping marketing team to personalize every piece of content they produce. With the shift of marketing from a paid media era to retention era, marketing team are trying to personalize each content they produce, ranging from newsletter to product description to blog descriptions, everything you can see on the website. So this is what we are doing at Newton. We're helping brands create content that will matter to us.
And from the tech perspective, we are basically starting from a prompt template, which is a sentence that includes learnable tokens. And we give this sentence to a language model that basically produces text from it. And then we project it into a stylistic space, that basically an embedding space that includes stylistic features of natural language. And we are learning the best tokens that minimizes the features between the text that has been produced and the text corpus features that we're trying to replicate the tone of voice of. And that's how we manage to replicate the tone of voice of every Newton's client.
This is it. Thank you.
Thank you.
All right, visual. Okay.
So, hi everyone, my name is Theo. I've been working for Visual for over a year now, and I'm here to talk about the limitation of Gen AI and especially GANs and diffusion models. So, in our company, we are creating an interactive styling experience where customers can create their outfits on their favorite web page. When the company was created a few years ago, they started to use GANs, but they quickly realized that this was not the right solution for our problems. There are many issues with GANs, especially text strings. Recently, there have been a huge step toward generative AI with diffusion models, but there are quite some issues. We basically lack controls. And looking at these results, it was not the right solution for us, for our problems. So what we end up doing is completely dropping all the generative network in our pipeline to create an entire generative engine based on image generation techniques such as image warping. We even developed our own physical engine. And that's pretty much it. This is a QR code that you can scan to look at our results and feel free to ask.
All right. Do you have this? So next one is Awen.
Yep. Hi, everyone. So you should start by knowing that in creative industries, the search for great ideas is both painful and costly. Creative teams spend up to 70% of their time generating prototypes on which 8 on 10 are thrown away, leading to exhaustion, stress, and frustration. For companies, it's a lot of investment, both in resources, salary, also waste and overproduction. Now, we believe that AI is very well positioned in its ability to generate, synthesize, and iterate on content to help humans not create just faster, but better. Nonetheless, creative workflows are by nature contextual, both in knowledge and style. which isn't necessarily represented in foundational model. This is why we actually collect our users' data across different media formats, for now text and image, which we fine-tune on diffusion and LLMs and redeploy in our app for consistency and applicability. We are developing your digital assistant to help generate, develop, and share your best ideas. Customizable and secured for your data, but also multimodal to enhance creativity and collaborative to boost productivity. Thank you.
Hi everyone, I'm Lucien Maman. I'm the co-founder and CTO of Flipit, and we use generative AI to unlock consumer engagements for brands in digital era. So what we're building is a no-code tools enabling marketers to create AI characters in a few clicks that will help you connect with digital native audiences. To do this, we leverage generative AIs in many ways in our solution. First of all, we have an approach, a text-to-virtual character approach that allows you to facilitate the creation of 3D and interactive characters. And in fact, with just a textual description, we take care of generating the full characters from its look, the visuals, but also its personality and all its characteristics that you can redefine at your convenience without any technical skills. And once you're ready, your character is set, we help you with our integration to put it in virtual environments where this is where your consumer will interact with it. And that's where we leverage generative agents to coordinate the dialogues, gestures, and actions within this 3D environment, connecting the dots between what's being said and how it is being said. And this is a first step toward true co-speech gesture generation, where the dialogues and gesture will be co-generated within the same model to actually improve the human virtual character interactions. Thank you very much.
All right, so the 14th edition of XCI is coming to an end. So first of all, I want to thank again all of the speakers who made time this evening to be with us and all the time to prepare the slides also.